What if your landfill is not just a compliance obligation, but an energy asset hiding in plain sight? Today, I want to leave you with one clear idea. A landfill can become an energy asset instead of a liability. Not by adding one technology, not by chasing trends, but by integrating gas collection, power generation, heat recovery, and water treatment into one coordinated system. Cumberland County Improvement Authority did exactly that. Everything I'm going to show you fits under one principle: control. Control what you already have. They control their gas, they control their heat, they control their water, and they control their power. Most landfills operate in a regulatory framework that defines success as meeting emission standards, managing leachate, and maintaining permits. But Cumberland County chose to reframe that baseline. They transformed a traditional landfill operation into what they now call an energy hub. They did not do it with speculative technology. They did not rely on subsidies, but instead they did it by integrating systems that were already required to operate. This is ultimately a story about control, integration, and disciplined execution. Most landfills collect gas and flaring. That satisfies regulatory requirements. Methane is destroyed, emissions are reduced, but economically, the value stops there. Cumberland County looked at the flare and they saw unused fuel. They looked at purchased electricity and they saw an avoidable cost, and they looked at exhaust heat and they saw untapped thermal energy. The unexpected move here was not installing generators. It was recognizing that the compliance system was already halfway to an energy system. Let's look at the specifics. The landfill sits on 275 acres in Millville, New Jersey. That's about 45 miles southeast of Philadelphia. It receives roughly 540 tons of solid waste every single day. There's approximately 160 methane wells. They run about 145 of them actively at any given time. The generators produce 20 million kilowatt hours annually. To put that into perspective, that's enough power to run about 1,600 homes. Generators exceed 98% uptime. These aren't projections. This is not theory. For Cumberland County, this is operational reality. The 4.8 megawatt plant primarily powers the solid waste complex and its nearby admin offices. But they do sell excess electricity back to the utility grid. The project reduces about 15,000 tons of carbon dioxide annually. And that doesn't include the reduction of methane, which has a global warming potential of up to 84 times that of CO2. Controlled combustion through power generation creates both an environmental and an economic return. There's also a community dimension here. If you drive by a landfill and you don't smell an odor, that's a good day. Reduced flaring, reduced truck traffic, reduced visible emissions. Sustainability here is not abstract. It's something the neighbors are experiencing. Cumberland County entered its energy partnership around 2011 through a state bid process. The authority avoided upfront capital costs through private partner-funded energy power plant. Cumberland shared some of the costs on the public portions. The partnership spread risk and kept costs predictable. Ownership of the power plant has changed hands several times. It started with PP&L. They were bought out by Talon, then EPP. Now it's operated by NextEra. But today, they're considering buying out their energy partners. The structure has allowed the authority to leverage private technical expertise while limiting capital exposure. The estimated annual economic impact of the microgrid is about $13.5 million. Importantly, operations are still funded through tipping fees and related revenue, but not taxpayer subsidies. It all begins at the surface. One of the important operational practices of Cumberland County is the use of rain covers. Now, rain covers are normally thought of as a leachate control tool, but they're also a gas management tool. When stormwater infiltrates the landfill, it increases the moisture content within the waste mass, and that moisture increases the leachate generation and can dilute the methane within the gas stream. So by increasing rain cover, the authority reduces stormwater infiltration. Less water entering the waste mass means less leachate formation, of course, but it also means more stable gas environment underground. The more stable the methane concentration, the more stable the combustion stability at the engine. Landfill gas is already variable, so anything you can do to reduce variability improves your uptime. The covers therefore serve multiple functions at once: reduce the leachate load and support gas quality. They are indirectly supporting generator performance. So here's how they do it. Cumberland is required to cover the fill with 12 inches of soil, and then they use a 20 mil geocomposite liner stitched together over top. But instead of using ropes and sandbags, they use the Wind Defender green mesh that goes over top of the black liners, which is uniquely designed to be held in place by the wind. Again, integration. A surface decision here is affecting subsurface chemistry, which also affects engine reliability and ultimately affects revenue. Covers are not just environmental controls, they are operational strategy. Now, gas management depends on how you collect it. At Cumberland County, there's about 160 methane wells with about 145 active at any given time. As the landfill expands, additional vertical wells are added. Vertical wells, they form the long-term backbone of the gas collection system. They're installed from the surface downward into the waste mass, and they remain active through later stages of the landfill development. Because methane follows anything penetrating the soil, the well is drilled down to the bottom and perforated pipe is installed all the way up, but no closer than 40 feet from the surface. Each well is about 200 feet apart to prevent overdraw on other wells, and they keep them 40 feet from the side slopes. Horizontal wells, by contrast, are typically installed during active filling. They allow early gas capture before the cell is fully built out. They can improve early methane recovery and reduce uncontrolled emissions in newer sections of the landfill. However, horizontal wells are sacrificial. They collapse under pressure as the fill gets deeper, and because they are used to catch early gas, they're best producers early on. But the pipe valleys get filled in with water, and there's no way to fix that. So there is a strategy component here. Horizontal wells support early capture, vertical wells support sustained collection. As waste mass matures, vertical wells become more critical to maintaining consistent gas quality and volume. Good power starts with good gas. Well field design affects oxygen intrusion risk, methane concentration stability, and total recoverable gas. It directly influences combustion stability at the engines. That's why the site conducts frequent monitoring, including approximately 8 daily readings on key wells, and holds monthly performance reviews. They actively service 145 wells. Older wells are decommissioned as they stop producing, and the authority monitors 85 wells for gas quality using the Loci Well Watcher system. This saves hours of manual checking every day. So the authority uses the automated wellheads on 50 wells, and they take 8 samples per day. Cumberland meets then with Loci monthly to discuss trends. What they've found is that oxygen intrusion is their biggest enemy. They keep service techs and spares on site and conduct proactive maintenance, and gas quality is managed intentionally. It's not just assumed. It's important to understand that landfill gas is not pipeline gas. It's roughly half methane and half whatever comes out of the land. Sulfur compounds, xylozanes, moisture. Variability is a constant reality, and the engine selection matters. So according to Steve Gabriel, partner with EPP, you need a very robust engine to actually take care and destroy the gas and make electricity. They did a lot of research, and they found that Caterpillar had a very robust type of engine that could handle biogas at the landfill. Other landfills tried to do this as well with other engines, but the Cat engine's unique, and they said there's not a lot of manufacturers that have a product that can handle landfill gas. Reliability here was not optional, it's foundational. Today, the system maintains better than 98% uptime. What did they install? It was 3 Cat G3520 generator sets. It's a 4.8 megawatt landfill gas to energy facility, but they didn't stop there. They built and operate their own microgrid. During the design, they found that in order to run at greater than 80% uptime, they would need a gas supply of 1,400 SCFM. But they're not running at 80%, they're running at 98% uptime. How did they do it? Well, originally they planned to run 2 engines and keep a third one in reserve, but instead now they just run 3 engines at a reduced power factor. because what they found was if they have an engine, if they're running two and they have an engine unexpectedly go down, it takes time for that third engine to start up and it reduces their uptime. But if they're running three engines at reduced load, an engine goes down, those two remaining engines can pick up the rest of the load. It turns out that downtime now is only for planned maintenance. The next opportunity emerged from simple observation. The engines were producing continuous exhaust heat, and that heat was going to be unused. So let's do a quick review of basic engine heat balance. The total fuel energy entering the system, whether it's gas or diesel or some other fuel, only 30 to 40% is turned into mechanical work. Mechanical work then is turned into the electrical work. The rest is released in the form of heat. 25 to 35% internal to the engine, 30 to 35% is released through the exhaust, and around 5 to 10% is just radiated off of the engine. At the same time, the site was treating about 100,000 gallons of leachate per day through reverse osmosis, creating roughly 30,000 gallons per day of concentrated waste that had to be hauled away 40 miles. Nearly 1,500 truckloads per year left the site. It was cost, it was emissions, it was risk. But what they did was capture the generator exhaust heat. They redirected it into a leachate evaporation system. Waste now is becoming working capital. So working with Heartland Water Technology, the authority installed the Heartland concentrator system. The Heartland concentrator is a patented process. It uses the exhaust heat from the power plant for evaporation, creating an energy-efficient cogeneration solution. So the exhaust streams from the generator are ducted under negative pressure into the concentrator where thermal energy evaporates the leachate concentrate. The system now evaporates between 28,000 and 32,000 gallons of leachate concentration per day. Combined with reverse osmosis, the overall reduction in raw leachate volume is about 98%. Hauling now only exists in the case of an emergency or some sort of planned maintenance. Here's an overview of how the concentrator works. Engine exhaust enters the column on the left and is ducted into the mixing chamber where the leachate is atomized. The mixture passes through a three-stage mist eliminator and the water vapor exits the stack. The concentrated leachate is recycled through the evaporation process. Heartland advertises 5% residual. The authority has experienced as low as 1% residual. So when you step back, the energy hub rests on four integrated systems: gas collection, power generation, heat recovery, and leachate evaporation. None of these technologies are revolutionary on their own. The value comes from integration. Gas flows to the engines, generators produce electricity, engines produce heat drives evaporation, and the microgrid distributes power on site. Each system reinforces the other. What about renewable natural gas? Well, it was evaluated. The site's volume and scale cleanup and pipeline economics did not support renewable natural gas as an optimal pathway. Electricity generation provided better alignment with available gas qualities and infrastructure realities. They needed to have about 3,000 SCFM of renewable natural gas in order to sell it. The lesson here is not that renewable natural gas is inappropriate. It's that it has to be a strategic fit more than trend to chase. Each landfill must evaluate scale, capital, and market access independently. This transformation required a mindset shift. Instead of asking, how do we comply? Leadership began asking, how do we control our energy destiny? Control meant owning electrical infrastructure. Control meant reducing dependence on hauling. Control meant internalizing energy flows instead of exporting value. Sustainability became an operational strategy, not just environmental messaging, not just a compliance expense. And they're not done yet. Future plans include expanding vertical wells, increasing rain cover to reduce leachate formation, developing an enterprise energy zone, and potentially supporting EV charging infrastructure. So what began as a straightforward waste to energy installation has now evolved into a comprehensive energy platform. Every landfill deals with methane. Every landfill manages leachate. The strategic decision is whether those streams remain costs or become assets. Cumberland County chose integration. They captured what they already had, they used it fully, and they built an energy hub in the process.